Now let's try this problem. So it says the anvil of a forging hammer that weighs 5,000 Newton is mounted on a foundation that has a stiffness of 5 exponent 6 Newton per meter and a viscous damping of 10,000 Newton seconds per meter. During a particular forging operation, the top, that is the falling weight, or you can call it hammer, weighing 1,000 newtons, the weight of the hammer is made to fall from a height of 2 meters. So the height of the hammer is 2 meters onto the anvil. This is the anvil, capital M. If the anvil is at rest before impact by the hammer, determine the response of the anvil after the impact, assuming that the coefficient of restitution between the anvil and the top is 0.4. So what do we need to find? Determine the response of the anvil after the impact. So the first thing we can do is we use the conservation of momentum and that the coefficient of restitution to find the initial velocity of the anvil, and yeah, just apply the conservation of momentum system of the system. So let's say we have let v t1 and v t2 be the velocity before the impact. That's a velocity of hammer before and after impact. And let's VA1 and VA2 the velocity of anvil before and after impact. Now using that we can apply the conservation of momentum. So that says the total initial momentum should be equal to total final momentum. So we have m va2 minus m va1 equals to m vt1 minus m vt2. Because if you take all of this on each side, it becomes total initial momentum becomes equals to total final momentum. Uh, uh, since the velocity of anvil in the beginning was 0, at t1 va1 equals to 0 because it was at rest, and v10, so we can determine the velocity of the hammer using the potential energy that it stores, that is equals to half mvt1 square, half mv square equals to mgh, right? Where we know h was equals to 2 meter. So the kinetic energy just before the impact of the hammer is equal to total potential energy that hammer was storing when it was at height 2 meters. So when it came to the height equal to 0, the total energy, potential energy has been converted to the kinetic energy. So at that point, the kinetic energy at height equal to 0 is equal to the potential energy that was stored in the hammer before. So from here, you can input the values of mass, and so we have the weight for this one. You can find W equals to mg for the hammer. For the anvil, the hammer is 5,000 newton, the anvil is 1,000 newton, and you can do some calculation for this one. So from here you can find vt1 equals to under root 2 gh is equals to 2 into 9.81 into 2, that is 6.26099 meter per second. That's a velocity of the hammer just before the impact. So now substituting this one into our equation, let's call it equation A. Now substitute this one into equation A. So it becomes, it was m va2 minus va1 equals to mvt1 minus mvt2. Oh, sorry. So you can substitute this value. The m would be equal to 5,000. That is the mass of the hammer divided by 9.81. That's the weight of the hammer divided by 9.81 to get the mass value. VA2 we want to find out. VA1 is 0 equals to m, that is 1000 divided by 9.81. That is the mass of the anvil, into Vt1, that is a velocity just before the impact. We have just find out 6.26099, and after it has hit the anvil, we don't know what's the value of that one. So we can substitute these values and find out the, if you just solve this one, 5000 over 9.81, that becomes 510.204. VA2 equals to 1000 divided by 9.81 into 6.260. It becomes 638.87 minus this into VT2, 102.0408 VT2. Now here, because they provided us the coefficient of restitution, we can use that value of 0.4. You know the coefficient of restitution is equals to R equals to minus of VA2 minus VT2 divided by VA1 minus VT1. So just start substituting the value. 0.4 equals to VA2 we want to find out, minus VT2, and VA1 is 0 and minus VT1 is 6.26099. Now we can substitute either VA2 in terms of VT2 or VT2 in terms of VA2. So because we are interested in the velocity of the anvil, response of the anvil, so we will find the VA2. Just find out the 6.638.87 minus 102.0408 VT2 divided by 510.204. That's the value of VA2, and you can substitute this one in this equation. So after solving it, you will have VT2 plus 2.504, and you can substitute the values and get your solution. VA2 equals to 1.460 8 meter per second, and vice versa. You can find the VT2, that is minus 1.043 meter per second. So that's the velocity of anvil before and after. And in fact, what they want us to find, determine the response of anvil after the impact. Just make another copy. So the initial condition we have, because to get the total response, initial condition we have is x of 0 at time 0 is 0, and velocity at 0 is, at time 0 is before the impact, is 1.46089. This is the point when the motion starts. So that's the beginning starting velocity. So we know the damping coefficient is equals to C over 2 km. That becomes 1000 divided by 2 into, that's the spring constant, that's 5 into 10 exponent 6 into 5000 divided by 9.81. So that makes up 0.09899. That's the damping coefficient for us. So from here you can find the damp and the undamped natural frequency. So the undamped natural frequency would be equals to under root k over m. Damped natural frequency would be equals to omega n into 1 minus damping ratio square, damping coefficient square. So that becomes equals to 5 exponent 6 divided by mass is 5000 divided by 9.81. that is 98.99 radians per second. That's angular frequency. You can substitute this one in this equation. 98.99 into 1 minus 0.0989 square, it becomes 98.0247 radians per second. So that's, we know the natural frequency, we know the damped natural frequency, we know the damping coefficient. So the displacement of our system we can directly find out using the, what's the case we have, because our damping ratio, this damping coefficient is less than 1, so it is a case of underdamped system. So it's an underdamped system since this damping coefficient is less than 1. So we can use our directly use this solution we have seen earlier. This one has the final solution becomes, so you have all of these values, you know x naught, you know the damping coefficient, you know the natural frequency, you know the damped natural frequency. So you can substitute all of these values. You know the value of x dot of 0, that's velocity in the beginning. And once you substitute these into the equation, sorry, so we will have it as E exponent, the coefficient, damping coefficient omega n t, that's x dot of 0 into omega d, that's the dimensional frequency to sine omega dt. We know the omega d is equals to 1 minus square whole into omega n. So if you substitute all of these values, it becomes e exponent minus 9.799 t into 0.0149 sine omega d, that is 98.99, oh, sorry, 98.024, 98.0247 t. That's the response of our system. This is how far the anvil will go. You can solve this one for any time. For time 1 second, 2 second, 3 second, it will tell you the response of the system. So this is how you can use the real systems and apply the fundamental dynamics and statics of the system, and just classify that system, either it's a underdamped, it's overdamped, or it's a critically damped system, and directly use those equation instead of driving the whole solution every time. You can directly use this one. So as you have seen, this method, that's quite lengthy, although it gives you the time response in the time domain, how, what will be the position of the system after x t amount of time, after t seconds, but it's kind of a very lengthy method. And we will see in the future how we can use a Laplace transformation to quickly solve these systems in few steps compared to this lengthy systems or solution method of critical characteristic equations.